All right, so condensed states, liquids and solids. Um, well, what do you know about liquids and solids? Well, what do you know about gases for that matter? So, if you have a gas, you've got molecules that are moving around, they're far apart, and the reason why they're far apart is because they don't cling to each other. They don't cling to each other because they don't have very strong attractions towards each other. Liquids are moving around. They do have strong attractions for each other, and that's why they all cling to each other. But they're able to move around each other. Solids attract each other very strongly and are fixed in place and thus cannot move. Right? So the attractions for particles in a solid are the greatest. So liquids and solids are what we call the condensed states. Gesundheit. They're the condensed states because they're basically as close, the molecules are as close to each other as they can be. All right, whereas gases, they're very far apart. So the term we're going to be talking about is intermolecular attractions. So intermolecular attractions is attractions between discrete molecules. Here's one molecule of HCl, here's another. If there's an attraction between them, we call that an intermolecular attraction, sometimes called intermolecular forces. This is different than the bond that's inside the molecule. So this bond right here between the hydrogen atom and the chlorine atom, technically this is going to be a polar covalent bond, and the bond that holds atoms together are called intramolecular. Right, so the prefix intra means within, right? Whereas inter means between. Intra is within the molecule. Very different things. So the bonding we've talked about so far was essentially intra. Today we're talking about inter. We're going to be focusing on attractions between molecules. So consider boiling water as an example. All right, so here's a beaker of water, and these are the water molecules. So when you add enough heat, you know that water boils. So the water molecules, they get enough kinetic energy, and they're able to leave, right? They're able to break whatever attractions they have towards each other, and then they just kind of shoot upward, up into the air. What they're actually doing is they're breaking the attractions between molecules, but the molecules themselves are not broken. The water molecule is intact. We do not break the bond between the hydrogen and the oxygen. Okay? So, the intermolecular attractions are London dispersion forces, dipole forces, and hydrogen bonds. There are others, but these, I bolded molecular because these are the primary attractions in covalently bonded compounds. The other attractions we'll be talking about are not considered covalent. They're other things. So, okay, let's talk about the first. The first is what we call London dispersion forces. And a London dispersion force arises because in any atom or molecule, the electron movement is independent. Right? Each electron moves at a rate and direction unrelated to other electrons. So at any given time, the electrons that are present in an atom, they may appear to be evenly distributed, or they might appear to kind of all be towards one side, right? And then a split second later, they might be skewed towards a different side, right? So because they're moving independently, there's no way to predict where they're going. They're just randomly moving. And so the result of that is when they are moving, if you were to take imagine taking a high-speed camera and just taking several high, pictures. At any given time, in any one of those snapshots, you might see the electrons huddled towards one side versus the other. So what I'm drawing here, this is delta negative and delta positive, right? So these guys, these indicate partial charge. Right? And I stress the word partial because they're not full charges. What you're looking at here is not ions. They're just molecules that, one side might temporarily be kind of negative and the other side might temporarily be sort of positive, right? But because of the random nature of the electron movement, there is fluctuation continuously, right? These are constantly fluctuating, and so the electrons, as they're constantly moving, produce these temporary dipoles, we call them. Right, a temporary dipole. Dipole means polar molecule. So regular atoms can be temporarily polar. And nonpolar molecules can be temporarily polar. So let's take a look at a simple molecule, right? Something like bromine. Right? Of course, bromine consists of two atoms, so its electrons at any one given time can be centered, or they might be like skewed towards one side, right? If these are the nuclei right here, because of the random electron movement. So this side up here would be delta negative, this side here would be delta positive, because the area of greater electron density is where the negative charge would be. Right, that makes sense, right? That's where all the electrons are huddled, right? So that's where your delta negative charge would be. Okay, so key points about London dispersion forces. They are temporary. It's caused by random movement. Okay, and it's also the only intermolecular force that non-polar atoms or molecules have. All right, so if something is nonpolar, like you've drawn your Lewis diagrams, you know how to build molecules. If you assess something as nonpolar, then the only attractive force that it could possibly have towards another molecule would be a London force. Okay, so what are some factors that affect the London forces? Well, the first would be shape. And the shape affects the dispersion forces because the London forces are highly dependent upon surface area. So if we look at this example here. Okay, so this molecule is pentane, so C5H12. And if you were to draw a Lewis diagram of it, we just by habit draw all of our Lewis diagrams as straight lines, but the reality is the bond angles means they're not actually straight, they're kind of more zigzaggy, right? So it's like this, right? And imagine a carbon at each of these vertices, and the hydrogens would be like, just going to put them as dots here. And next thing you know, your diagram looks something like that. So, when molecules are relatively flat, like this one, right, long skinny molecules that are relatively flat, that means there is a large surface area. I swear that word says area. Okay, large surface area for dispersion forces. Okay, so imagine these little green squigglies being dispersion forces at work. You take two molecules, line them up next to each other. If they're both long and flat, there's lots of spaces for dispersion forces to take place. Okay? But contrast that. What if your molecule is something like this? Okay, so this is also C5H12, but the structural bonding is different, right? But the same number of atoms, hydrogen and carbons are there. Okay, I don't want to draw all the hydrogens, but it's the same formula. But because of its different bonding structure, it's more of a spherical shape. It's not really flat. So there's less points of contact of surface area between molecules. I should say less effective dispersion forces. Let me edit that. Less effective dispersion forces. All right, Leslie. Does that make sense? You ever hang a really large poster, right? You're going to need lots of tape, right? Lots of surface area. You're able to put up more tape. It's going to stick better, right? So, same idea. Okay, the other factor is simply mass. All right, larger atoms, larger molecules have larger electron clouds that are easier to polarize. All right, what does that mean, polarize? Well, the word polarize means to become polar. So if you compare a small atom with a small electron cloud versus a larger atom with a larger electron cloud, the larger the electron cloud is, then the greater dipole moment, even if it's temporary, that can be formed. So these could look like this, right? So that little guy, how strong of a dipole moment really would there be? This would be the delta positive side. This would be the delta negative side, but its total dipole moment strength really wouldn't be that much. But the larger atom, if its electrons kind of shifted in a similar manner, right? So you could get a much more significant dipole moment taking place because of the larger electron cloud. All right? And this doesn't just go for singular atoms. This goes for molecules. A molecule with a large formula has got lots more electrons, meaning it can make much stronger dispersion forces. And this is reflected in a boiling point. Right? Here are the boiling points for neon, argon, krypton, and xenon. Right? These are all noble gases. And if you just simply look at its position on the periodic table, neon in period 2, argon in period 3, krypton period 4, xenon. Of course, the number of protons goes up, but what we're focusing on here is the number of electrons. The more electrons there are, the higher the boiling point will be, because the stronger the attractive forces are. Right? So higher boiling point means more energy needed to get them to turn into gas. And then halogens here, right? Halogens are all diatomic in nature, the Hunkelgriffs, F2, Cl2, Br2, I2. So much so, in fact, when you look on the periodic table, fluorine and chlorine are red letters, so they're gas. But find bromine. What color is bromine on the periodic table? Right here. The letter's blue, so it's liquid, right? So this one's liquid, and iodine is what color? It's black, so it's solid. Right? So it's reflected very simply in that one family, the halogens. You see it go from gas to liquid to solid. The boiling points increase because they're all nonpolar molecules, The only attractive forces they have are dispersion forces, and when the dispersion forces get stronger and stronger, that's when your states change. Are we okay with dispersion forces? Okay. So dispersion forces are the only force present in nonpolar molecules. And you should understand how dispersion forces will change. The greater the mass, the more electrons, more polarizable it is. Yes, Ron?
So dispersion forces, they would also be present in polar molecules, right?
Correct.
All covalent?
They're pretty much present in all molecules. It's just that we pay attention to dispersion forces in nonpolar molecules because that's the only ones they have. Okay? All right, the second type is the dipole-dipole attraction. So I mentioned before that the word dipole means polar molecule. So the dipole attractions are the attractions between polar molecules. The difference is that these are permanent dipoles. Permanent meaning the molecule's polarity does not change. It stays polar because of its structure, right? The hydrogen chloride molecule right here, right? The hydrogen and chlorine, this molecule is permanently polar and nothing will change that because you literally only have two atoms, the hydrogen, the chlorine on opposite sides. There's net dipole moment will be directed towards the more electronegative element, right? So chlorine gets the delta negative and the hydrogen is the delta positive. You'll see me drawing these arrows a lot, right? These represent the dipole moments, right? The head of the arrow points to the more electronegative element. Okay. So these little green squigglies here, or these green dots, represent the dipole-dipole attraction. The reason why we say dipole twice, because it's the attraction between two dipoles. All right, and there's other types of attractions that involve dipoles. They're called other things, but a dipole-dipole attraction is an attraction between two polar molecules. Okay, let's look at another example. So in this molecule, notice how the shape, right? So we've got the formula CH3CN. The blue is the nitrogen, the black is the carbon, and the whites are the hydrogens. So this molecule is, if you were to draw a Lewis diagram of it, maybe it would kind of look like a straight line, right? But what's more important is that it has each one of these has a net dipole moment. And as such, an attraction will be made. The negative side of one molecule attracts the positive side of another, and this happens continuously throughout. So guess what happens when two molecules have the same side facing each other, meaning like two molecules have their negative sides facing to each other? What do you think happens? Like if this happened, right? So if these two molecules kind of butt up towards each other, you've got a delta negative side next to a delta negative side. Yep. All that's going to happen is that it's going to flip around. The like charges repel, the opposite charges attract. Okay? All right, so like here, for example, on this side. Here with that's happening a couple of places. Here you've got the delta negatives next to each other. No big deal. This molecule or this molecule will just flip around. This guy here will flip around, right? Okay. So there's the second attraction, intermolecular attraction, called dipole-dipole attractions. Happens in polar molecules. Well, guess what? Polar molecules also have dispersion forces. So these molecules have dispersion forces and they have dipole-dipole forces. But there's a point we need to make here. If two molecules are of comparable size, right? The read on that is same amount of electrons. So if they have the same number of electrons, then the dipole-dipole interaction will be the main attractive force, or at least the one that you're focusing on. Okay? You have to remember, think of it as like a controlled experiment, right? If you're going to compare the attractive strengths between molecules, if they both have the same thing, you're focusing on what's different. Okay? So a couple of examples of that. So, actually, right here. Nitrogen, diatomic nitrogen, right? Diatomic oxygen. These two are both similarly sized because they're right next to each other. If we counted up the electrons, you're talking about, 14 nitrogen, 14 electrons in nitrogen, and 16 electrons in oxygen. So because they've got roughly the same amount of electrons, just different, a slight amount, their boiling points are pretty close to each other. So first and foremost, does that make sense? Do you guys understand why oxygen has a slightly higher boiling point than nitrogen? Because it's got a couple more electrons. They're both nonpolar molecules. But nitrogen monoxide has 15 electrons, which is right in between nitrogen and oxygen, right? It's in between 14 and 16. But the difference is that this is polar, right? Whereas these are nonpolar. And the fact that it's polar means it has dispersion forces and it has dipole-dipole. And that's why its boiling point is higher than the other two. It's not the heaviest one of the bunch. It just has the additional dipole-dipole attractive force. So the attractions between nitrogen monoxide molecules are greater than the attractions between nitrogen molecules. Okay, so in this set, we were comparing a situation where it's all similarly sized. Okay? Let me give you some more examples. What if one molecule is much larger than another? All right, so let's compare two molecules like CH4, which is methane. Right? If we draw out CH4, you can imagine this is a tetrahedral. This is polar and nonpolar. Is methane polar or nonpolar? Yeah, it's nonpolar. It's nonpolar, which means it only has dispersion forces, right? It's got dispersion forces. Okay, but what if we compare that to heptane? All right, and I'm gonna just draw these as hydrogens. Well, clearly that's much bigger. Is heptane polar or nonpolar? That is nonpolar. So they're both nonpolar. So that means they are both subject to dispersion forces, but clearly one has way more mass than the other, is more electrons, more polarizable. Heptane is actually a liquid at room temperature, whereas methane is a gas. Which means methane at room temperature has not been boiled yet. That is why it is a liquid, because it has not reached the boiling point. Okay. Let me give another example. Well, here, I'll just throw this one into the same grouping here. HCl, hydrochloric acid. Right, hydrochloric acid is, when we say hydrochloric acid, we mean the solution of, but HCl, the molecule HCl itself, is a gas. Right? The molecule is, 2 atoms. It's polar, which means it's going to have dipole-dipole attractions. And yet it's a gas. Why does HCl, with its supposedly stronger dipole-dipole, why is this a gas, but heptane, with its weaker dispersion forces, is a liquid? Yeah, why?
I guess in some rare cases, the redundant dispersion forces in heptane are so much stronger than the dipole-dipole forces, or override the dipole-dipole forces in the HCl molecule, since heptane is so massive.
Right. Yeah. It's like, there's, first of all, the size comparison is stark. Huge size compared to a small size, right? So when you start comparing things that are not the same sizes anymore, the whole which type of attractive force is stronger it becomes irrelevant. Just the larger it gets, intermolecular forces really add up. It's like a grassroots campaign, right? If you go fundraising and ask every person you know for $1, and then everyone that they know asks someone for $1, that can all add up pretty quickly, as opposed to you just getting $20 from your friend. That's a terrible example, but does that make sense? I guess, like a Ponzi scheme. You ever heard of a Ponzi scheme? Like where there's a pyramid where like one person like tells other people to get money, and then they tell other people to get money, and it's like a pyramid and all the money flows to the top. They're like highly illegal. Anyways. Okay, so then there's hydrogen bonding. So hydrogen bonding is essentially, it's a dipole-dipole. Okay, it is a dipole-dipole attraction. It's just got its own name because categorically it's stronger. It's much stronger than your typical dipole-dipole. Okay, so same idea as dipole-dipole, but stronger. So why is it stronger? Here is why. Well, first of all, there's a requirement. There must be hydrogen bonded to nitrogen, oxygen, or fluorine. Okay, specifically, there must be hydrogen in a molecule bonded to one of these three elements. And it must be polar. So I guess that's two requirements. Right? First requirement, second requirement. So here's what happens. When you have a very electronegative element like fluorine, okay, so let's say we have a molecule like HF, okay? Fluorine is so electronegative that the electrons that are in this bond are really, really pulled towards fluorine compared to hydrogen. So how many electrons does a normal hydrogen atom have? Just one. So if this electron right here belonged to hydrogen, and it's way more attracted to fluorine than hydrogen, that means the nucleus of hydrogen is essentially exposed or unshielded. Okay? So the large electronegativity difference between, in this case, fluorine and hydrogen results in an unshielded positive nuclear charge on hydrogen. And that means it's like a way more positive charge than normally would be found. I need a different color here. It's a much larger partial positive charge. And that thing just, it attracts the negative ends of molecules so strongly. Right? So other HF molecules are just drawn to it in droves. That's hydrogen bonding. Okay? It's got to be a polar molecule because there has to be asymmetrical electron distribution, and it has to be specifically hydrogen that is bonded to one of those, either fluorine, oxygen, or nitrogen. It won't work if it's other atoms, because the whole point is you need that nucleus of hydrogen to be exposed to cause such the strong positive partial charge. Okay? So, here's some examples. You need to understand where hydrogen bonding is actually taking place. So the hydrogen bond, in this case, the water molecule, the oxygen is the negative, and the hydrogen on a neighboring molecule is the positive. In the case of hydrogen fluoride, it's between the fluorine, which is the negative, and the hydrogen, which is the positive. In the case of ammonia, same thing. You can have hydrogen bonding between dissimilar molecules, like ammonia and water. They don't have to be the same molecule, right? If one of the molecules presents hydrogen bonding, it can have a hydrogen bonding effect on other molecules. So another example, water. Okay, so water, it's got its dipole moments, and it's, in this direction and this direction. This is the delta negative side. This is the delta positive side. Okay. Another polar molecule that that's not water, like HCl. HCl can hydrogen bond with water because the hydrogen on water is so partially positive, it's almost like fully positive. Right? It's that strong that it attracts the delta negative side of HCl. Yes, question.
Can the hydrogen bond only occur between hydrogen and nitrogen, oxygen and fluorine?
The hydrogen bond can only exist if it's one of those specific elements combined with hydrogen, correct?
Then how would HCl be a hydrogen bond?
So the hydrogen bond is the attraction here, okay? And we don't need both molecules to literally have hydrogen bonding, as long as the one of them does. That the attraction between the partially positive or the very positive hydrogen here attracts other polar molecules. This is still considered a hydrogen bond. Just like these are all hydrogen bonds. Now, these examples here, literally both molecules have hydrogen bonding, right? So it's kind of slam dunk. It's obvious that that's hydrogen bonding, that's hydrogen bonding, that's hydrogen bonding, that's hydrogen bonding, right? But if one of these molecules were to bond with anything else that were polar and relatively highly electronegative, that would also be considered hydrogen bonding. Now, I should mention, well, actually, I don't know. Never mind. I won't mention it. I was going to say something, but it might end up confusing you because there's some debate in the AV community about another potential element being added to the hydrogen bonding list. Well, I wonder if you guys can come up with it. What else is highly electronegative? Chlorine. So chlorine is they're considering maybe we should count chlorine because chlorine forms bonds, intermolecular attractions that are just about as strong as the hydrogen bonding found between nitrogen, oxygen, and fluorine. Like almost. So the cutoff, it's like arbitrary. It's like gray. Okay. But classically speaking, all textbooks cite hydrogen bonding occurring when the hydrogen is bonded to either nitrogen, oxygen, or fluorine. Okay, so let's look at an example of what hydrogen bonding can do. Here is a simple compound, H2S. H2S is a bent molecule. H2SE is a bent molecule. Here, I'll draw it. H2S, H2SE, H2TE. Right? They're all bent, right? The lone pairs are here, okay? They all have dipole moments. And of course, here's water, which is bent. Look at the boiling points. If we ignore water for a second and just look at those three compounds, H2S, H2SE, and H2TE, does it make sense that H2TE of those three has the highest boiling point? If so, why? Why does H2TE have the highest boiling point of those three? Let's start by identifying the attractive forces. Everything has dispersion forces, right? Okay, what other dispersion force, if any, do they have?
They all have dipole-dipole.
They're all polar molecules, so they all have dipole-dipole, right? So they're polar and they have dispersion forces. So the fact that they're polar, that's kind of a constant amongst all three, so let's ignore that for a second. What is the other difference between these three molecules? Yes. Greater dispersion forces here. Right? He has more electrons than Se. Se has more electrons than S. So, of course, of these three, H2T is going to have the highest boiling point. But, dun dun dun, bring in water. Isn't oxygen the smallest out of sulfur, selenium, and tellurium? Yet look at its boiling point. It's 100. It's 100 degrees greater than the heaviest of that family. Or at least the heaviest of the one shown here. What is the reason? Hydrogen bonding. Okay, so a water molecule, by all rights, if you judge it just based on mass and dispersion forces, this shouldn't be a liquid. Right? No other compound that light is a liquid. Right? But not only is it a liquid, it's a tough liquid. It takes a lot of energy to boil water because of the strong hydrogen bonding it has. Okay? All right. Okay, so I guess the last thing for today. Induced dipole. Induced dipole molecules are when you have a polar molecule that can influence. Polar molecules can influence electrons in a nonpolar molecule. That's what the word induced means, right? So you could have like HCl, right? Delta negative, delta positive, come into proximity of another nonpolar molecule like bromine, for example, right? So bromine is normally nonpolar, but by proximity, the result is I'm going to draw this as just an oval. The electrons in bromine will be shifted. They're internally going to be skewed and pushed because of this. The negative side of that polar molecule is influencing the electrons in a nonpolar molecule, causing the nonpolar molecule to be temporarily polar. It's induced. Okay? The difference is that it's a permanently polar molecule that started this, as opposed to a nonpolar molecule like in traditional dispersion forces. All right, another example. Ion dipole forces. It's exactly what it sounds like. It's the attractive force between polar molecules and ions. And this is why ionic compounds are so soluble. The ions attract water, either a cation or anion. It attracts water very well. Because of that, it's easy for ions to be pulled apart and separated in solution. Okay, it's actually one of the main driving forces of why solutions form. It's because of the strength attraction between ions and water. Okay, that's enough for today.